Something happened during NASA's Artemis 2 mission that most people completely overlooked, not because it was hidden, not because it was classified, and not because it wasn't important, but because it didn't look dramatic enough in the moment. And that's precisely why this matters. When something goes obviously wrong, it instantly becomes a headline people can point to and say, that's the problem. Subtle things, however, that don't look like imminent failure, move differently, and slip through unnoticed. In space missions, those unnoticed moments are often the ones engineers go back to analyze frame by frame and only later realize those were the moments that changed everything. And I want you to stay with me on this video because by the time we reach the end, you are going to understand what Artemis 2 actually was, not just what it looked like from the outside. There is a version of this mission that the mainstream coverage gave you: launch day, the splashdown, a few spectacular photos, and then it was over and everyone moved on. But underneath those 9 days in deep space is a story about engineering, risk, human decision-making, and the slow, patient construction of something that could change the future of our species. And I think that story is worth telling properly. So if you are new here and you want deep dives into space science and exploration that go further than the headlines, this is the channel for you. Hit subscribe now and make sure you don't miss what's coming. Now let's get into it. On the first day of April 2026, NASA's most powerful operational rocket lifted off from Kennedy Space Center in Florida just before sundown. On board the Orion spacecraft, a vehicle that the crew had named Integrity, were 4 astronauts. Commander Reed Wiseman, a naval aviator and former ISS crew member. Pilot Victor Glover, making history as the first black astronaut to travel beyond low Earth orbit. Mission specialist Christina Koch, the first woman in human history to travel this far from our planet. And Canadian Space Agency astronaut Jeremy Hansen, the first Canadian to venture into deep space. 9 days later, on the evening of April 10th, their capsule came screaming back through the atmosphere at over 24,000 miles per hour and hit the surface of the Pacific Ocean off the coast of San Diego in what Mission Control described as a perfect bullseye splashdown. The crew was safe, the spacecraft had survived, and within hours, NASA officials were standing in front of cameras in Houston declaring this the start of a new era of human exploration. Now that phrase, new era, is the kind of language that gets recycled so often it stops meaning anything. But in this case, it is not a press release talking point. It is an accurate description of what just happened. And here is why. For 54 years, from December of 1972, when the last Apollo astronaut stepped off the surface of the moon and climbed back into the lunar module, all the way to April of 2026, every single human space mission stayed close to Earth. The International Space Station orbits at roughly 250 miles above the surface. The space shuttle never went further. Every Soyuz mission, every cargo run, every spacewalk, every science experiment conducted in orbit, all of it happened within what is effectively the backyard of our planet. And the reason that matters is not just symbolic. It is deeply practical. In low Earth orbit, everything is relatively manageable. If a system fails, there are options. Communication with Mission Control happens almost in real time. The psychological pressure of isolation, while real, has a ceiling, because you can always see Earth out the window, enormous and close, and on a bad enough day you could in principle be back on the ground within hours. But the moment you push beyond that boundary, the entire equation changes. Communication delays grow, radiation levels climb dramatically because you move outside the protective bubble of Earth's magnetic field. There is no quick abort option, there is no emergency return. And every decision, every system call, every engineering response to an anomaly carries a weight that simply does not exist when you are a few hundred miles above home. Artemis 2 went 250,000 miles away, and it did so with 4 human beings inside, for the first time in more than half a century. And that is not a small thing. That is the point where theory becomes reality, where ground simulations stop being good enough, and where the gaps between what engineers expect and what space actually delivers begin to reveal themselves. And Artemis 2 revealed several of those gaps. Some of them made the news, some of them did not. And I want to walk through each one carefully, because together they paint a picture of exactly where this program is and what it is quietly building toward. Let's start with the one that got the most attention for the least serious reasons. The toilet broke. I am not going to minimize this, because the way it unfolded actually tells you something important. On the very first day of the mission, before the spacecraft had even completed its initial maneuvers out of Earth orbit, the crew reported a fault warning on the waste management system. Mission Control worked through it with the crew and managed to restore basic function. For a few days, things seemed stable. But then a second issue emerged. The system that vents processed liquid waste out into space was not performing anywhere near its expected output rate. The vent was delivering a fraction of what engineers had predicted. Attempts to diagnose it started simply. Maybe ice had formed in the external nozzle in the deep cold of space. The crew reoriented the spacecraft so the nozzle faced the sun. Internal heaters were activated along the relevant lines, and still the blockage remained. Then the crew reported an unusual smell coming from the hygiene area. Engineers tracked that down to what was likely insulation material near the door of the compartment, but the investigation was logged and continued. The leading hypothesis by the time the crew was heading home was that a chemical compound used to prevent bacterial growth inside the waste system may have undergone an unexpected reaction, generating debris that had lodged in a filter. But when the flight director was asked directly about the root cause, his answer was blunt. They did not have one yet. The investigation would continue once the spacecraft was back on the ground and engineers could physically get inside and examine it. Now, why does a broken space toilet matter beyond the obvious discomfort for 4 people living in a small capsule for 9 days? Because this was the first time this waste management system had ever been used by human crew in a real deep space environment. Everything prior to this mission was simulation and ground testing, and the system behaved differently in the actual environment than it did in any of those tests. That gap between predicted behavior and real-world behavior is data. That data will directly influence the design of the same system on every future Orion mission. And future missions are going to be much longer than 9 days. If this issue had not surfaced here, it could have surfaced on a mission where the crew was weeks away from Earth with far fewer options. So the toilet that broke is not a punchline. It is the early warning system working exactly as it should. But that was not the most significant anomaly that emerged during the mission. Not by a considerable margin. For that, we need to go back to 2022, and a problem that was uncovered after the uncrewed Artemis 1 test flight, a problem that, 4 years later, engineers are still working to fully solve. When the Artemis 1 Orion capsule was recovered from the Pacific after its lunar test flight, the post-mission inspection of its heat shield revealed something unexpected and concerning. The ablative material used to construct the shield, a substance designed to gradually burn away in a controlled manner during atmospheric re-entry, carrying heat with it and protecting the capsule, had not behaved as models predicted. In more than 100 separate locations, sections of the material had not melted smoothly. They had cracked and popped off, breaking free from the surface in an uncontrolled way. This is the opposite of what the shield was designed to do. A heat shield is not just important. It is the final physical barrier between a crew of astronauts and temperatures that would incinerate them in seconds. If it fails in the wrong way, at the wrong moment, there is no recovery. There is no escape system that can activate during atmospheric re-entry at those speeds and altitudes. If the shield goes, the mission ends. Period. Artemis 2 flew with a heat shield that was essentially the same design as the one that had already shown this flaw. NASA did not hide this. They acknowledged it openly and repeatedly, including in briefings with the crew, who were involved in the investigation process from the beginning. The decision not to delay the mission for over a year to retrofit a completely redesigned shield came after a review of all available data, consultation with outside experts, and a conclusion that engineers now understood the mechanism well enough to work around it. And the solution they arrived at was not what you might expect. Instinct would tell you to reduce the heating on the shield, to come home more gently, more slowly, to apply less stress to a material you know has a vulnerability. But the actual fix was the opposite. engineers redesigned the re-entry trajectory to apply heat more consistently and more intensely, shortening the phase where the capsule briefly rises back up through the atmosphere before making its final descent. The reason: that temporary cooling phase was allowing the outer burned layer of the shield to become rigid before the gas trapped beneath it could fully escape, and the pressure was eventually forcing sections of material to fracture and break free. By maintaining higher and more consistent temperatures throughout the descent, the material stayed more pliable, the gas could escape progressively, and the cracking risk was significantly reduced. Commander Wiseman, when asked about this before the mission, was clear-eyed about it. He and his crew had sat in rooms with the engineers who ran this investigation. They understood the physics. They understood the residual risk. And they chose to fly. When the capsule came home on April 10th and hit the water, aircraft tracking the re-entry had already begun capturing heat shield imagery from the air. Divers in the water photographed the exterior of the capsule within minutes of it arriving on the surface, and the analysis that follows will directly shape the redesigned heat shield being built for every subsequent Artemis mission. The data from this re-entry is not a postscript. It is the primary scientific objective of the return journey. Now, there is a third anomaly I want to talk about, and this one received almost no mainstream attention at all. During the mission, a persistent and unexpected leak was detected in the part of the spacecraft's propulsion system that pressurizes the oxidizer supply for its maneuvering thrusters. On the ground, this system had been tested extensively, and the leak rate measured was small and considered within acceptable limits. In the actual flight environment, the measured leak rate was 10 times higher than anything seen during ground testing. Not slightly elevated, 10 times. An order of magnitude, and engineers had to sit with that information and make a series of decisions in real time about what it meant. What it meant in the immediate term was that the spacecraft could still perform all of its required burns. It did, without any issues throughout the flight. But what it meant for the future was clear. This valve system is going to need an extensive redesign before it can be trusted on missions where the stakes are significantly higher. And now here is where I want you to think carefully about what happened next, because this is exactly the kind of thing that gets glossed over, and exactly the kind of thing that I think is most worth understanding. The engineering team, as the crew was making its way back to Earth, took a decision. There had been a manual piloting demonstration planned for the return leg of the journey. This was an exercise where the crew would use the spacecraft's onboard navigation sensors and reaction control thrusters to manually maneuver Orion relative to another object, a test of the kind of precise crew-guided flight that will be critical in future missions when docking with lunar landers near the moon. The team canceled it. They gave up that test objective in order to dedicate the available time and crew attention to characterizing the valve leak as thoroughly as possible before splashdown. The reason was simple but telling. The service module, the component that houses those valves, does not come home. It separates from the crew capsule just before re-entry and burns up in the atmosphere. The data you collect during the flight is all you get. You can examine the crew module after recovery, but those valves are gone. So engineers made a deliberate trade. They sacrificed one planned test to maximize the data gathered on an unplanned problem. That is not a sign of things going wrong. That is a sign of a team operating with exactly the right priorities. Now let's step away from the engineering for a moment and talk about what the crew actually experienced out there. Because 9 days in deep space, far beyond any human mission since the Apollo era, produced moments that are difficult to describe and that deserve to be communicated properly. On the 6th day of the mission, April 6th, the Orion spacecraft reached the moon, and in the hours before the formal flyby observation period began, the crew crossed a threshold that had stood for 56 years. Since April of 1970, when the Apollo 13 crew swung around the moon on an emergency free return trajectory after their famous explosion, the record for the farthest any human being had ever been from Earth had never been broken. No mission had gone further. No crew had ventured into deeper space. Artemis 2 passed that mark and kept going, reaching a maximum distance of just over 252,000 miles from Earth. And in that moment, Commander Wiseman asked Mission Control for permission to do something unplanned. He and his crew had identified 2 craters on the near far side boundary of the moon that had not yet been officially named. They asked that the first be named Integrity, after the spacecraft that had carried them there, and they asked that the second be named Carol, the name of Wiseman's wife, who had passed away from cancer in 2020. Wiseman was overcome as Canadian astronaut Jeremy Hansen made the formal request over the radio. All 4 crew members embraced in the cabin of the spacecraft, floating weightless 250,000 miles from Earth, in tears. That crater now bears her name. It will bear it for as long as the moon exists. The flyby itself lasted 7 hours, and what the crew observed during that window was scientifically extraordinary. They documented craters, mapped surface geology, noted the sharp distinction between the sunlit and shadowed regions of the lunar surface, and described what they saw in real time to scientists listening from Earth. They observed Earthset, watching our entire planet sink below the moon's horizon, a direct echo of the Earthrise photograph taken by the Apollo 8 crew in 1968, one of the most famous images ever captured. And they witnessed something that, by any reasonable definition, no human eyes had seen before. As Orion swept around the far side of the moon, the spacecraft, the moon, and the sun aligned in a precise geometry that produced a total solar eclipse, seen not from Earth, but from deep space, with the moon appearing roughly 5 times larger than it does from the ground. For nearly 54 minutes, the 4 astronauts watched the sun disappear completely behind the lunar disk, leaving only the faint glow of the solar corona visible as a halo around its edge. Stars became visible that are normally impossible to see with the moon so close. Light reflected from Earth gently illuminated the darkened lunar surface. And during that window, while scanning the dimly lit terrain below, the crew reported 6 separate flashes of light, meteoroids traveling at tens of thousands of miles per hour, striking the moon's surface and releasing the energy of their impacts as brief bursts of visible light. Scientists back on Earth reportedly reacted with audible excitement when that data came through. Pilot Victor Glover, attempting to put what he was seeing into words for Mission Control, said that humans had probably not evolved to perceive what was in front of him. He told the ground that it was truly hard to describe, and even listening to the audio of that exchange at a safe distance from the experience itself, you can hear the weight of genuinely having no adequate language for what is in front of you. And then the capsule came home. The most dangerous 13 minutes of the entire mission, back through the atmosphere at 24,000 miles per hour. The heat shield doing what it was designed to do, under the watchful eye of tracking aircraft and the data recording systems aboard the spacecraft. And on April 10th, at just after 8 in the evening Eastern Time, Integrity hit the surface of the Pacific, and NASA called it a perfect descent. Now here is what all of this amounts to. Because I have spent this video walking through anomalies and technical concerns, and you might be wondering whether the overall picture is one of concern or confidence. And the answer is both, in the right proportions. It is confidence that the engineering process is working correctly, that the mission found the problems it was designed to find, that the team made the right decisions in real time, and that the crew came home safely. And it is clear-eyed acknowledgement that significant technical work remains before the next step is taken. That next step is Artemis 3, currently planned for 2027, which will test the docking of an Orion spacecraft with lunar landers in Earth orbit. Both SpaceX's Starship and Blue Origin's Blue Moon lander are competing for roles in the missions ahead. And after that, Artemis 4, targeted for as early as 2028, will be the mission that actually returns human beings to the surface of the moon for the first time since 1972. Not a flyby, a landing. 2 astronauts setting foot on the surface near the moon's south pole, in a region of extraordinary scientific interest. And the reason that specific location matters so much comes down to something as simple and as profound as water. In the permanently shadowed craters near the lunar South Pole, places that have not seen direct sunlight in billions of years, where temperatures plunge to the lowest levels found anywhere in the inner solar system, There is strong evidence for the presence of water ice, preserved in the deep cold over geological timescales. And that water ice is not just scientifically fascinating, it is potentially the most strategically valuable material in the solar system right now. Because water can be broken into hydrogen and oxygen. Hydrogen and oxygen are the components of rocket propellant. If you can extract fuel from the moon's surface, you no longer have to launch all of your propellant from Earth, which is the single most expensive and limiting factor in deep space exploration today. Access to lunar water ice does not just enable missions to the moon. It potentially enables missions to Mars and beyond, using the moon as a refueling and staging point, rather than requiring every gram of fuel to be lifted out of Earth's gravity well. And this is why the long-term vision of the Artemis program is not just about planting a flag and coming home. It is about building infrastructure, establishing a gateway, the planned orbital station near the moon, as a base of operations, developing surface habitats, creating the conditions for extended human presence in a way that builds on itself rather than resetting with every mission. Every anomaly that Artemis 2 uncovered, every system it pushed into a real environment and found wanting in some way, feeds directly into that future. The toilet that did not vent properly will be redesigned. The valve that leaked 10 times worse than expected will be rebuilt. The heat shield will be replaced with a better one. And the manual piloting test that was canceled will be rescheduled and completed under better understood conditions. This is what sustainable space exploration looks like from the inside. It does not look like a clean series of achievements. It looks like a methodical accumulation of hard-won knowledge, some of it gathered through anomalies you did not predict, and all of it pointing toward a future that is not yet fully visible but is clearly being constructed. At the post-splashdown press conference, NASA's Orion program manager stood in front of the cameras and said something that I think deserves to be remembered. He said, "This is the start of a new era of human space exploration." And NASA's administrator, Jared Isaacman, called Artemis 2 the opening act. Not the headline performance, not the culmination of something, the opening act. And that framing matters, because the extraordinary thing about this moment in the story of space exploration is not what just happened. It is what it enables. The crew that flew Artemis 2, Wiseman, Glover, Koch, and Hansen, were not just the first humans to venture into deep space in 54 years. They were the people who stress-tested the vehicle that future crews will rely on. Every piece of data they generated, every system anomaly they documented, every photograph they took of a world 250,000 miles away, every tear shed in a spacecraft above the moon's far side, all of it belongs to the next crew, and the crew after that, and every mission that follows in this slowly accelerating chain of human exploration beyond our planet. Canadian astronaut Jeremy Hansen, just after his crew broke the distance record, radioed back to Earth and challenged this generation and the next to make sure that record would not stand for long. That is the spirit that Artemis 2 represents. Not a completion, a beginning, not a ceiling, a new floor. And when you understand that, when you trace the line from the toilet that broke on day 1 to the crater named for a commander's lost wife, to the heat shield analysis already underway, to the redesigned valves being engineered for future missions, to the water ice waiting in the permanent shadow near the moon's south pole, you start to see the shape of something being assembled across time and mission by mission. Something that on any single day might not look impressive enough to make the evening news, but something that, viewed across the arc of what it is building toward, is quietly one of the most significant undertakings of our era. And that is the story of Artemis 2. Not the launch, not the splashdown, not even the eclipse seen from the far side of the moon. The story is in everything that happened in between, in the data that came back, and in what engineers are doing with it right now, so that when the next crew straps in and lights the engines, the machine they are trusting with their lives is a little bit more understood, a little bit less uncertain, and a little bit closer to being exactly what it needs to be. That is how you build the future. One mission at a time, one anomaly at a time, one decision at a time, quietly, methodically, and further from Earth than anyone had been in 56 years.